Okay, we're going to talk about natural logarithms some more, and to find the inverse function, we replace y for f of x. We switch x and y, so now they're different functions, and we solve for y, and so the exponent of e that gives us x is y, and now y is by itself. I'll replace y with f inverse of x, and that equals log base e of x. And just like log base 10 has a special name, it's like log without the 10, log base e is ln. You might have seen that on your calculator. So that's going from the original to the inverse. Okay. Now this is different. We're going to take this expression and rewrite it as an exponential function. So the exponent of e that gives us m, that exponent is n. And so we can rewrite the log base e as ln. This is just converting the exponential to a log. This is finding the inverse function. So in the first column here, we have the x values, which are the exponents. If we put those x values into the exponent, -2 gives us 1 over e squared, -1 reciprocal 1 over e, e to the 0 is 1, e to the first is e, to the second, to the third, to the fourth. And each time we're multiplying by e. That's our growth factor. Here is the inverse function, that if x is 1 over e squared, what made 1 over e squared? Well, the exponent of -2 made 1 over e squared, because this is asking for what is the exponent that makes this. How do I make this? Exponent of -1. How do I make this? Exponent of 1. Again, the exponent of e that gives us x. That gives us x. And you can see that these are inverses of each other. Looking at the x values, the growth factor is x. Looking at the y values, the growth factor is multiplying by e. That's like switching the domain and the range. In sketching our log graph, here's our old friend 1, 0. The exponent of e that gives us 1 is 0. And then we also have the point 1, the exponent of e that gives us c, which is 2.7, is 1. So we have these 2 points, the base of our log and that point 1, 0. And we draw our graph. Our domain goes from 0 to infinity. Our range goes from -infinity to infinity. The cave is pointing down. It's concave down from 0 to infinity. It's always increasing from left to right, starting at 0. And behavior. As I go to the right, the y goes to infinity. As I go to the left and I approach 0 from the right side, y goes to -infinity. We use the knowledge we learned in graphing other logs. The base 2 log, at 1, it's 2. At 10, at 1, it's 10. For the base 5, at 1, it's 5. And at e, at 1, it's 2.7-ish. And so looking at this graph is going to be the taller one, this graph is going to be the shorter one, and so from 2 to 10, 2 is the bigger one, 10 is the smaller one, this is 2.7, this is 5, so the smaller one is the 10, the biggest one is the 2, the next biggest one is the 2.7-ish, and the third one is the 5. Again, let's read this. The exponent of e, that gives us 2, that exponent is k. The exponent of e, that gives us x, is 5. The exponent of e, that gives us k, that exponent is x. The exponent of e, that gives us k, is a. The exponent of e, that gives us 1, well, the exponent that gives us 1 is 0. The exponent of e, and if this expression has a base e, what is the exponent of e? Well, it's 3. And the same thing here, we have 4 times something. Let's hold the 4 off. This is saying what is the exponent of e? We'll look over here. Fortunately, there is an e with an exponent of 5. So the exponent of e is 5 times 4 is 20. And you're right. In these last two examples, this has to be an e for us to do this as easily as we did. If it's not an e, we can't do that as easily. Again, using transformations, we have our base graph of y equals ln of x, or natural log of x. We have our 1, 0 point, and we have our 2.71 point. That's our base. E is about 2.7. So this is our basic graph. And then we move it to the right 2 and up 3. This point goes up 3 to the right 2. This point goes up 3 and to the right 2. And to the right 2 is also where our new asymptote is. And here's our graph. B is slightly more complicated. Like we did earlier, I need to separate the reflection from the shift. So I factor the negative out, and I'm left with x minus 1, right? Because this is still negative x, and this is still plus 1. So, again, our basic graph, 1, 0, and 2.71. Here's our basic graph. It's going to shift to the right 1. Afterwards. Let's do something else first. Let's first do the reflection. So if I do the reflection, this point goes here, and this point goes here. I'm not going to draw it. Well, I will draw it. So here is our reflected graph with the negative. Okay? Then that graph is going to get stretched by 3. Well, if that's 0, multiply 0 by 3, it's still 0. But this 1 multiplied by 3 gets to be 3, and we're here. I made a correction. So if I take this point and move it to the right 1, I'm here. I take this point, move it to the right 1, I'm here. And here is our stretched, reflected, and shifted graph. The domain from left to right, this one 2 to infinity, This one, negative infinity to 1, bottom to top. Pretty boring. So we did this earlier. Let's remind ourselves of the strategy for finding the inverse function. We first of all replace f of x with y. We switch x and y. We solve for y. And then we replace y by f inverse of x if the original function is f. Just make sure these two letters match. So if I have this function, I switch in this case, m and n. I solve for m, the exponent of b that gives us n. That exponent is m. So finding the inverse, we go through our steps very carefully. Replace f of x with y. Switch x and y. Divide by 3 to get the log by itself. And then the exponent of 2 that gives us y plus 1. That exponent is x over 3. And then to get y by itself, we subtract 1. And replace the new y by f inverse of x. For b, we replace f of x by y. We switch x and y. And there's lots of negative signs here. So what I'm going to do is the term that has the y, I'm going to move it to the left so that it's positive. And the x on the left, I'm going to move it to the right. So I'm slowly getting y by itself. Then the exponent of 2, that gives us negative x minus 1. That exponent is y minus 2. And then to get y by itself, we add 2 to both sides, and then we replace y by f inverse of x. Again, we need to isolate the ln pretty soon, but first of all, f of x becomes y. We switch x and y. Then I multiply both sides by 2 to isolate the log statement. Then the exponent of e, that gives us 1 minus y. That exponent is 2x. And to get y by itself, I'm going to add y, goes to the left. I'm going to subtract the e minus 2x, it goes to the right, and that's our inverse function. The y is replaced by f inverse of x. Replace f of x by y, switch x and y. The exponent of 1/4, that gives us x. That exponent is y plus 3. To get y by itself, I subtract 3, or add a negative 3 to the left-hand side, and I forgot to write f inverse of x for my new function, because this y is not the same as this y, because when I switched them, they are different.